Hi everyone. So the next part of the topic that we'll be looking at is periodic trends. We've just covered electron configuration so far. So the exam questions and what you need to know is be able to explain each of these four periodic trends. There's two parts to it. You need to be able to identify the trend, okay, so which going across or going up on the periodic table, does each of these factors increase or decrease? But you also need to explain why they occur. So atomic radii, so the radius of atoms. Okay, what's the trend? Do they get bigger as you go across or smaller and so on? Ionic radii, so the radii of ions, ionization energy and electronegativity, which we'll explain a little bit more about those later. To be able to explain the trends of these, you need to understand and use these terms because these are the factors that affect atomic radii and so on. So the first thing is nuclear charge. That's the number of protons in a nucleus. So that should be relatively self-explanatory. But here is a carbon atom and a silicon atom to compare. Carbon has 6 protons in its nucleus, therefore it whereas silicon has 14. Therefore, carbon has a smaller nuclear charge than that of silicon because it's got 6 positive protons. Silicon's got 14 positive protons. Okay, so when you compare carbon and silicon on the periodic table, they're directly above each other. So silicon has a greater nuclear charge as it has more protons. That nuclear charge, the bigger the nuclear charge means the stronger the pull on those negative electrons. Okay, so the bigger the nuclear charge, the more protons, the stronger the pull on the outer and all the electrons, in fact. The next factor that we need to consider is the number of energy levels. Again, we compare carbon and silicon. Another way of describing the number of energy levels is the distance of the valence electrons from the nucleus. So with carbon, there are 2 energy levels. Okay, the outermost electrons are in the second energy level. Therefore, compared to silicon, which has 3 energy levels, carbon's outer electrons are closer to the nucleus compared with silicon, simply because silicon has 3 energy levels, so therefore those outer ones are further away. If we were to then compare with something that has 4 energy levels, so for instance, if we go back to our periodic table, carbon, silicon, germanium, if we were to compare that, that would have another energy level, so therefore its outermost electrons have a greater distance to the nucleus. The third factor that affects each of these periodic trends is shielding. This is when the inner energy levels of electrons reduce the effect of the positive attraction from the nucleus and the valence electrons. Let's go to our same examples, carbon and silicon. Now, carbon's outermost electrons, okay, are in the second energy level. They are being attracted or pulled towards the nucleus because the nucleus is positive and these electrons are negative. If you have a look, there is 1 energy level of electrons between the outermost and the nucleus, as represented by these 2 electrons here. So what happens is these inner electrons, they shield this outer electron and essentially reduce the nuclear attraction between the nucleus and those outermost electrons. They shield or block and they get in the way, essentially. If you compare that with silicon, because this is the key, is we are always comparing 2 or 3 elements. If you compare with silicon, its outermost electrons are in the third energy level. Therefore, they have 2 energy levels of inner electrons that are going to shield or block the outermost electron from that nuclear attraction from the silicon. So we would say that silicon has higher shielding than carbon, okay? Because it's got 3 energy levels, therefore it has 2 inner energy levels, and therefore those 2 inner energy levels of electrons are shielding the outer one. Okay, so let's go back. You'll be asked to describe these periodic trends, and you do so using these 3 factors, okay? The next video, we're going to have a look at atomic radii specifically. All right, thank you, everybody. Bye.